Hi all, today we have the theorem 2. In this theorem, we will discuss an important subspace of vector space called the trivial subspace. Let V be a vector space, a subset containing only the zero vector. So, if you consider a subset of V consisting of only zero vector, this we will prove this is always a subspace. That is so easy because if you consider the characterization of the subspace, we need to verify two closure properties. First, we need to verify 0 plus 0. This is clearly 0 is an element of S, and alpha times 0, that is equal to 0 as well as an element of S. Then these two statements together imply that S equal to singleton set 0 is a subspace. So this proves theorem 2. Now we have theorem 3. Theorem 3. The statement of theorem 3 is a non-empty subset S of a vector space V is a subspace of V if and only if whenever U, V and two arbitrary elements of S and alpha beta are two arbitrary constants, then this alpha U plus beta V belongs to S. That means theorem 3 is also a characterization of a subspace. So this theorem 3 combines two conditions given in the first theorem, and it gives a single condition to verify that a subset is a subspace. Okay, so first we prove by assuming the subspace S is a subspace, then we can easily prove this one, and we'll prove the converse as well. So first we assume S is a subspace. Okay, then we have S is a vector space. Then we have alpha belongs to alpha is a scalar. As it is a vector space, we can say that alpha times U belongs to S for all alpha and U. Similarly, beta V belongs to S for all beta and V. So from these two, we can write alpha U plus beta V belongs to S for all alpha comma beta for all scalars anyway, and U comma V belongs to S. So this shows that whenever S is a subspace, then alpha times U plus beta times V is also an element of S for arbitrary scalars alpha and beta, and two arbitrary elements U and V. So this is the first part. For the second part, we need to assume this condition. If we choose any alpha and beta are scalars, and U for any two arbitrary elements U and V belongs to S, we can get this sum as S. We need to prove that S is a subspace. In order to prove this S is a subspace, we use theorem 1 again. So to prove S is a subspace, we will prove two closure properties. Okay. So first closure property, put alpha is equal to 1 and beta is equal to 1, uh, and U comma V belongs to S. Okay. Then hypothesis, this is our assumption. This assumption says that 1 times U, that is U, 1 times V, that is V, belongs to S. So this proves the first closure property. Similarly, the second one, by taking alpha is equal to alpha as well, and U is U, and beta is equal to 0 and V is equal to 0, implies we can get alpha times U plus 0 times 0, that is 0 again, that belongs to S. So this proves the second closure property of the scalar multiplication. So as satisfies, by this condition that satisfies two closure properties, then we can say that this S is a this non-empty subset S is a subspace of V. So this proves theorem 3. So these two theorems are very important. So please go through it. And now we have some examples on this theorem. Then we can move on to examples. To begin the first example, we consider this set. We need to verify that this is a subspace of P square. What is P square? P square is this is the set of all polynomials of degree at most 2. So at most 2, and along with zero polynomial. So this is our P square. This P square is always a vector space. We need to verify this subset is a subspace of P square. But we know that when you consider the zero polynomial, then zero polynomial is always an element of P square. We need to verify that this zero polynomial is an element of this set S. But in order to verify that, we find zero polynomial at the point 2. We can get zero polynomial gives 0 at every point. So this implies 0 of t does not belongs to S. Then S does not contain 0. So we can say that this S is not a subspace. Not a subspace. Then we have another example. Next example is U is equal to 1, 2, 3, and consider a subset such that alpha times 1, 2, 3. Okay, that is set of all multiples of 1, 2, 3 with alpha is a scalar. In order to verify this is subspace, we use we can take any arbitrary scalars d1 and d2 and two elements from this, that is alpha times 1, 2, 3 and beta times 1, 2, 3. So we can verify that d1 times alpha times 1, 2, 3 plus d2 times beta times 1, 2, 3. Okay, so we need to get this is also a multiple of 1, 2, 3. So we can write it as d1 alpha plus d2 beta, this is the scalar, times 1, 2, 3. So this is also an element of S, hence S is a subspace. S is a subspace. Next we have a definition of linear combination. Suppose we have a vector u. U is a vector in the vector space V. We say that u is a linear combination of elements of V, say V1, V2, etc. Vn in V if u can be written as some scalar times d1 times v1, d2 times v2 plus etc. dn times vn. Then we can say that this u is a linear combination of the vectors v1, v2, etc. vn. So this is an example of, this is the definition of linear combination of elements. So once you given any two numbers u1 or any k numbers u1, u2, etc. uk, then d1 times u1 plus etc. dk times uk are called the linear combinations of the vectors u1, u2, etc. uk. Here we have di's are scalars. This is the definition of linear combinations. The next class we will discuss the properties of this linear combinations of vectors of V.